Hey, we're going to take a look at an electrolytic cell and how to do the calculations for those. So I've got this diagram that's given in the problem drawn. This is actually the last problem on the sample problem worksheet. It's supposed to be labeled as H. Looks like it's labeled as number 3. So anyway, you'll see this picture. We're given these half reactions with their reduction potentials. And again, on the AP exam now, you're not going to be given that full chart of reduction potentials. You're just going to be given something like this with just the potentials that you might need. So first off, we are asked, well, anyway, let's just explain what the problem says here. It says an external direct current power supply is connected to 2 platinum electrodes immersed in a beaker containing 1 molar copper sulfide solution at 25 degrees Celsius. So we have those standard conditions of 1 molar for our solution. Again, this is an electrolytic cell, so there's a power supply. You'll notice that this electrode is labeled as the copper reduction. And then we see bubbles drawn over here, which would imply that that's where the oxygen gas is being formed. And it says, as the cell operates, copper metal is deposited onto one electrode, and oxygen gas is produced at the other electrode. So you can see which one is which with the picture. 2 reduction and half reactions are given to us. And so now we're going to answer some questions. So first off, it says, on the diagram, indicate the direction of electron flow in the wire. So we know that electrons flow from the species that's being oxidized to the species that's being reduced. And so looking at these reduction potentials, well, you can see the reaction that they're giving me, and it looks like, again, if copper is being deposited here, this is the reaction that's happening over here, and they're looking at copper is the one that's being reduced, gaining electrons, but also looking at the potentials. Notice that copper's reduction potential is less than the reduction potential for this oxygen. However, this being an electrolytic cell means that it's the reverse of what we normally see in the regular galvanic or voltaic cells, and that is that this species is the one being reduced. And the way that that's happening is because we have this power source. So electrons are going, we should get a different color marker. Electrons are going from the oxygen side to the copper side then, because this is the side that's being reduced. And again, I know that from the wording in the problem. It says that copper solution is gaining, or the copper ions in solution is gaining 2 electrons, and it's depositing copper on the electrode. So I know that I have solid copper forming from ions, and so that's got to be the reduction reaction. So the electrons are coming from this side and back over to the copper side. So reduction is happening here, oxidation is happening here. Okay, so write a balanced net ionic equation for the electrolysis reaction that occurs in the cell. So the net ionic equation, so if this is being reduced, that's as written, this is being oxidized, so we're going to flip this around. And notice, before we go adding these 2 together, there's 4 electrons being produced from this oxygen reaction. So we're going to need to multiply this number, or sorry, this whole equation for the reduction by 2. So that when I add together my 2 equations, I have an equal number of electrons appearing. So again, this oxidation one is being reduced, so it's going to be 2 H2O liquid. So that's my only reactant once I switch these, plus 2 copper plus 2, plus, again, the electrons will be not shown. So that's 4 electrons canceling. And so then I end up with oxygen gas plus 4H plus, and that's going to be aqueous, plus the copper solid. Okay, and there's my balanced equation. So C is predict the algebraic sign of delta G and justify your prediction. So the fact that this is the way that it's happening, so copper's being reduced, this is being oxidized, so this we would call our cathode. Reduction happens at the cathode. Oxidation happens in the anode. When I go to find the E standard for the cell, that's the cathode voltage minus the anode reduction potential, and that gives me a negative voltage. That happens to come out to, I figured out, negative 0.89 volts. So the fact that the thing that's being reduced has a lower reduction potential, that's non-spontaneous. That's why we need this power source. So anytime we're talking about an electrolytic cell, we're talking about a non-spontaneous reaction. That would mean then that we'd predict that delta G would be positive, because again, we would be getting a negative voltage. And so again, how this thing actually gets going is because we have a power source supplying the energy to run the reverse reaction. So C is the algebraic sign of delta G. It should be positive because this is non-spontaneous, and I know that because, again, the copper has a lower reduction potential than the oxygen, and I end up with a negative E cell, so or E naught cell. So next we're calculating the delta G value, so I can put my calculations where my mouth is, and we know that delta G naught equals negative NFE standard. So number of electrons being transferred, 4 electrons. So again, before we added the two equations together, we figured out there were 4 for our value of n, so that's a negative 4 times, and again, the Faraday constant. I plugged in the whole, again, you might see this in the rounded form of 96,500, or this form. This is always coulombs per mole of electrons, and then again, this is technically moles of electrons. And then my E that I just found, that's a negative 0.89. Multiply all that together, again, voltage being in joules per coulomb. When I multiply all those values together, that gives me a positive value. So negative times a negative gives me a positive value. I'm going to keep it down to 2 significant figures because this number only had 2 significant figures. And so that's going to give me, well, it's 343,487 joules. And since I know you don't like to give me extra numbers, again, we'll convert that to kilojoules so that we can express our number with fewer placeholder zeros there. So 340 kilojoules is what we come up with for delta G. And again, delta G being positive, as we already discussed, is because this is a non-spontaneous reaction and we're forcing the reverse reaction to happen. All right, so lastly then, we've got to got an additional piece of information. So in these electrolytic cells, a lot of times what these are used for is to deposit, you know, if I want to deposit copper onto an electrode for a reason, you know, if I want to deposit silver onto jewelry or gold, you know, for gold plating on jewelry, this would be the method that you could use. And so I can figure out, you know, depending on what the current that I'm running this at and how long I run it for, I can figure out what mass is going to be there when I'm done. So we're going to, I'm going to erase this down here so I've got some space. And I'm going to keep my overall equation there. So the thing we have to look out for is if you can do the dimensional analysis setup, that's really all that these problems are involving the, you know, finding the mass. So it says an electric current of 1.50 amps passes through the cell for 40 minutes. So we've got our current, which you'll see the symbol I on the reference sheet. So I is for current, and that is 1.50 amps. You also might see this written as a capital A. But what an amp is charge per unit time that's being transferred. And so charge unit is in coulombs, and then the unit of time that we use is in seconds. So really 1.50 amps is the same thing as saying there's 1.50 coulombs per second that is passed through this cell because of that power supply. So then I'm told that this is run for our time of 40 minutes. Okay, well, and then lastly, I'm asked to calculate the mass in grams of copper that's deposited. So let's see how this is going to work out. So I know that this is the amount of charge per second that's passed, and I know that's done for 40 minutes. So what I'm going to do is, well, figure out how many coulombs was that got passed through this cell. So 40 minutes, well, let's do some unit conversion. So seconds is on the bottom. So for every 60 seconds, that's equivalent to 1 minute. Okay, so that will be, you know, coulombs per minute when I multiply that out. But since I like to do dimensional analysis, I'm just going to tack on my next. So coulombs per minute times the 40 minutes. And that will give me 3,600 coulombs have been passed through my cell. Okay, so having this then, what I know is, well, I know how many electrons per copper are passed, and I also know the charge of a mole of electrons, because that is what Faraday's constant tells me. So I'm going to get rid of this little time I marked down here. So again, just thinking about factor label method and what I know about, okay, so I have this many coulombs went through the system, and so that means then I can figure out how many electrons. If I know Faraday's constant, which is 96,485 coulombs per mole of electrons. So just in looking at the 96,485 coulombs per mole of electrons. So labeling it out so that I can see what I have. So if I want to eventually relate to, well, I know if I can get to moles of copper atoms, then I can get to the mass of copper, right? So we know that we can get from moles to mass. So how do I get to moles of copper atoms with this information? Well, I know for each copper atom that gets deposited on this electrode, that it's gained 2 electrons. So this Coulomb value that we got from looking at the current and the amount of time that was run, we can then figure out, well, I have a link between coulombs and moles of electrons. I know how many moles of electrons are for each mole of copper that's deposited, and then I can get to moles of copper. So 3,600 coulombs. This number is coulombs per mole. So I want the mole of electron to be on the top, so I'm going to be dividing by 96,485 coulombs. Again, I'm just going to do a factor label method here for dimensional analysis. So moles of electrons. So I don't want to go back to this whole balanced equation. I just want for every one copper solid that gets formed, it takes in 2 electrons. Okay, so my copper, every 1 mole of copper that gets deposited takes in 2 moles of electrons, right? I know that from this half reaction equation. Okay, so moles of electrons, that's been converted to moles of copper. Stoichiometry, we won't do that. So now I've got moles of copper. Well, I know how to get from moles of copper to grams of copper, and certainly you do too. So I'm going to use the molar mass of copper, which is 63.55 grams per mole, and multiplying all that out, I end up with 1.19 grams of copper. I'm keeping 3 significant figures because my original current only had 3 significant figures. And there you go. So that's how much will be deposited. So this is the trick. And again, relating how much charge got passed through. I know the relationship between charge and number of electrons using Faraday's constant. I can relate from the balanced equation the moles of electrons to the moles of copper that got deposited. And then I know the relationship between moles and mass for that particular type of atom. And there you go.